Hello, I'm Roberto Guanciale and I'm presenting a work on compositional information flow refinement. This is a joint work among KTH, Ericsson and CISPA. So I think it's well understood that modular verification based on some sort of refinement is fundamental to analyze complex systems. However, the relationship between information flow security and refinement is well known to be complicated. This is a common example where reduction of non-determinism cause information flow security problem in the refinement. So in the abstract model, we have three variables, x, y, and z. And the variable z is non-deterministically set to 0, 1. Now, the adversary here is some sort of process or agent that can only observe some variables in the system. For example, only the output or only some channels. Here we assume that are the variable y and z that are represented with red boxes. Now, in this abstract model, the attacker cannot learn anything about the variable x since the output is non-deterministically chosen, is randomly selected, basically. Now we can have two refinements of this model. On the left refinement, this non-deterministic choice is actually resolved accordingly to the value of the variable x. So if x is false, we will set z to false, otherwise we will set z to true. Now, we will probably consider this refinement non-secure, since there is a direct leakage from the variable x to the variable z that is observable by the attacker. And this leakage is not present in the abstract model. On the other side, the other refinement, and here for refinement that means some sort of trace inclusion, will be considered secure because the choice, the non-deterministic choice, is done accordingly to the value of the variable y. Now, the goal of this paper is to define when a refinement is secure and investigate compositionality properties of this refinement. So here for refinement, we mean a simulation between an abstract model and a refined model that can reduce non-determinism, as we have seen before, but can also add new variables that introduce observational power for the attacker. For example, imagine where your abstract model is your C programming language, where you have the variable x and y, and the attacker can only observe the variable y that may be the output of the system. And your refinement model may introduce additional hardware detail, for example, cache or the binary code implementation of your C program, or also other variable like execution time here t. Now, I will consider, for example, this refinement to be secure, since the execution time is a side channel that is only affected by the variable y that is already observable in the abstract model, while I will probably consider this refinement non-secure since the side channel here is affected by the variable x that was not originally observable by the attacker. So to give a semantic justification of secure refinement, we use the notion of ignorance or knowledge that has already been used before, for example, in knowledge-based security for dynamic policies. So given a run of a system, we define the ignorance of the run as all the other runs of the system that are observational equivalent for the attacker with the given run. So for example, suppose a program where we have three variables, x, y, and z, that writes into z the sum of all the three variables. And suppose that the attacker can only observe the third variable z here. If we take a run consisting only of the initial state, so this is basically the initial state of the system, where the attacker can only observe z, and suppose that initially here we have both x and y set to true, I here use just Boolean values instead of number for simplicity, then the initial ignorance of the attacker are basically these four states, where we have one state for every possible combination of value of x and y, since these are not directly observable by the attacker initially. Then, after one transition, the attacker learns that the sum of these three values is false, again, modulo 2. So, it means that the attacker learns that the two variables x and y must have the same value. They're either both false or they're either both true, since only in this case we can have exactly the same observation in the trace. So the ignorance basically shrink from four states to just two trace. And this is in fact why it's called ignorance, right? When this set shrink, the knowledge of the attacker increase. So we can use this to define when a refinement is secure. We say that a refinement is ignorance preserving, where for every pair of abstract trace and corresponding concrete refined trace, then the abstract ignorance is equal to the set of abstract traces that simulate the concrete ignorance. And intuitively, this means that the knowledge regarding abstract variable of the attacker is the same in the abstract model and refined model. And now we can use this to see why the original refinement that resolved non-determinism using the secret variable is non-secure. So if we take this trace in the abstract model, where the variables were false, false, and the public variable is non-deterministically set to false, well, the ignorance to this contains also this other trace because these two traces have exactly the same observation. While if we take the same trace here in the concrete model, we can see that the ignorance of this trace consists only of one trace because this other state cannot produce the same observation, because here the observation will be true instead of false. So in the abstract world, the ignorance consists of two traces. In the concrete world, the ignorance consists only of one trace. That means there is a leakage. Actually here, we directly leak the secret variable. And we can use the same to check why instead is secure to resolve this non-deterministic choice using the public variable. Because now if we take this trace, right, the ignorance of this trace contains again both traces. The trace where also the public variable was true because they produce exactly the same observation for the attacker. So this definition also covers the intentional leakage of abstract secret information. For example, suppose a system that is designed to leak if the input provided by the user match a password stored in the database to perform authentication, and also allow data refinement. For example, if we take the sum program that we've seen before, we can refine this with a new system where the variable x is actually implemented by adding two new variables a and b together. So the variable x is not present in the environment anymore, but instead we have these two variables that have to be summed together to get the original value of x. And we may also add an additional observable variable t. Let's say this is a timing side channel. And suppose, for example, that t is directly affected by this new variable a that contains part of the variable x. Well, even if we leak a in this example, we can show that this is an ignorance preserving refinement. In fact, if you do addition modulo some finite number, right? If you leak one of the two components that sum together give us x, do not directly leak x because the secret is basically hidden in the other part of the state component p. So one problem with ignorance preserving refinement is that these are usually non-compositional. In fact, if we take the system that we've seen before and we have shown that if we leak the variable a, we get an ignorance preserving refinement. Well, of course we get an ignorance preserving refinement even if instead of leaking a, we leak the other component b, that is just symmetric to the other case. But when we compose these two systems together, we get more leakage in the refined world. In fact, in the abstract world, we will leak basically the sum of x, y, and z, and twice the same sum. So this does not leak anything more than just the sum. While in the refinement, we will first leak the value a, and then we will leak the value b. And this is problematic, right? Because now when we compose the two ignorance preserving refinement together, we leak more in the refinement than in the abstract world, because by knowing a and b, the attacker also knows basically the value of x. So to solve this problem, we introduce an unwinding condition. We say that the triple of a pre-relation, refinement, and post-relation is a relational refinement if it satisfies three properties. So the pre-relation must imply observational equivalence for the attacker. Then the second property is that for every abstract state and corresponding concrete or refined state, if there is another abstract state A2 that is observational equivalent to A1, then there must exist a refinement of A2, that let's say C2, that is in the pre-relation P. And then finally, for every concrete trace starting from C1 and corresponding simulating trace starting from A1, if there is an indistinguishable, so observational equivalent trace starting from A2, then there must be another concrete trace starting from the refinement of A2 that we have called C2, that is in the pre-relation with C1, that is observational equivalent for the attacker with the original trace starting from C1. And also the final state has to be in the post-relation queue. Well, we show indeed that these relational refinements are indeed endurance preserving, and we show that if the post-relation is equal to the pre-relation of the second refinement, we can compose them together securely. In the work, we also provide two example applications, secure multiparty computation addition, and we show that oblivious memory, oblivious RAM is secure. One implementation of oblivious RAM is secure using refinement. We also show vertical composition that allows us to compose refinement vertically and add different information about the system at each layer. And finally, in the related work, we show that this is the first time that someone introduced an unwinding condition that allowed to reestablish compositionality, sequential compositionality of refinement when we allow data refinement. Thank you.